Understanding air defense systems, safeguarding the skies. Air defense systems are critical technologies designed to detect, track, and neutralize airborne threats, such as enemy aircraft, drones, and missiles. These systems play a vital role in safeguarding nations' airspace, protecting civilian populations, military assets, and critical infrastructure. With advancements in aerospace and missile technology, the importance of robust air defense mechanisms has grown exponentially. This video explores the intricate workings of air defense systems, delving into their components, operations, and the challenges they face in adapting to evolving aerial threats. By understanding these systems, we gain insight into one of the most crucial aspects of modern warfare and national defense. Air defense systems are complex networks composed of multiple interdependent components working together to detect, track, and neutralize airborne threats. These components can be broadly categorized into detection systems, command and control systems, and interceptor systems. Detection systems. Detection is the cornerstone of any air defense system, enabling early identification of potential threats. The key components include radar systems. Long-range surveillance radars monitor airspace for incoming threats, such as aircraft, missiles, and drones. Phased array radars provide high-precision and rapid scanning capabilities. Over-the-horizon, OTH radars extend detection range beyond the Earth's curvature. Electro-optical sensors. Thermal imaging and infrared sensors detect heat signatures from aircraft or missiles. Cameras and optical trackers assist in identifying and verifying targets visually. Satellite systems. High-altitude reconnaissance satellites monitor airspace on a global scale. Early warning satellites detect missile launches through infrared or other electromagnetic signals. 2. Command and Control C2 systems. The Command and Control C2 system acts as the brain of the air defense network, processing data and coordinating responses. Centralized communication networks. Integrates data from radars, sensors, and satellites into a unified operational picture. Facilitates secure and rapid communication between various units. Threat assessment systems. Uses artificial intelligence, AI, and machine learning to classify and prioritize threats in real time. Identifies whether detected objects are friend, foe, or neutral based on IFF, Identification Friend or Foe systems. Decision-making and target assignment. Determines the most effective interceptor for neutralizing specific threats. Allocates resources efficiently, ensuring timely responses. 3. Interceptor systems. Interceptor systems are the physical tools used to neutralize threats once detected and classified. Missile defense systems. Surface-to-air missiles, SAMs. Designed to intercept and destroy hostile aircraft and missiles. Examples include short-range systems, for example, MANPADS, and long-range systems, for example, S-400 Patriot. Ballistic missile defense, BMD. Targets high-speed ballistic missiles during various phases of flight, boost, mid-course, terminal. Anti-aircraft guns. Automated and manually operated guns designed to engage low-altitude threats. Often used in conjunction with radar for accurate targeting. Directed energy weapons, DDoS. High-energy lasers and electromagnetic weapons that disable or destroy threats without physical projectiles. Emerging technologies aimed at countering drones and other agile targets. 4. Support and auxiliary components. Power systems. Mobile and fixed power sources ensure consistent operation of radars, C2, and interceptor units. Mobility platforms. Many systems, such as SAM launchers, are mounted on vehicles to enhance operational flexibility. Maintenance and logistics. Continuous servicing and supply chains are critical to keeping air defense systems operational during prolonged conflicts. Detecting and tracking airborne threats is a fundamental capability of air defense systems. The process involves a combination of advanced technologies and methodologies designed to identify, classify, and monitor objects in real time. Here's how it works. 1. Threat detection. The first step in air defense is the detection of potential threats within the monitored airspace. Detection relies on sophisticated sensors and systems. Radar systems. Radars emit radio waves that bounce off objects in the sky, returning signals to calculate their position, speed, and trajectory. Types of radars. Surveillance radars provide broad, long-range coverage for general airspace monitoring. Target acquisition radars focus on specific regions to identify and lock onto threats. Phased array radars allow rapid scanning and tracking of multiple targets simultaneously. Electro-optical and infrared sensors detect heat signatures and visual characteristics of targets, such as aircraft engines or missile exhaust. Effective for stealth targets that radar might struggle to identify. Satellite-based detection. Satellites equipped with infrared or electromagnetic sensors detect missile launches and other high-altitude activities. Essential for early warning systems against intercontinental threats. 2. Classification and identification. Once a threat is detected, it is analyzed to determine its type and intent. Identification friend or foe, IFF, uses transponders to confirm whether an object is allied, hostile, or neutral. Helps prevent accidental targeting of friendly forces. AI and machine learning algorithms analyze radar and sensor data to classify threats based on size, speed, flight pattern, and radar signature. Distinguish between military and civilian aircraft, drones, and missiles. Flight path analysis tracks the trajectory and behavior of objects to assess potential threats. Sudden changes in altitude, speed, or direction can indicate hostile intent. 3. Threat tracking. After identification, the system continuously monitors the object to predict its behavior and determine the best interception strategy. Real-time tracking. Continuous updates on the target's location, speed, and direction. Multiple radars and sensors collaborate to ensure no gaps in tracking. Data fusion integrates data from various sources, including ground-based radars, airborne systems, and satellites. Creates a comprehensive and accurate picture of the threat environment. Predictive algorithms calculate the likely path of the threat based on physics and known flight capabilities. Assist in determining the optimal interception point and timing. 4. Counter-stealth and low-altitude threats. Modern air defense systems have evolved to counter stealth technologies and low-altitude attacks. Low-frequency radars detect stealth aircraft by identifying their unique disturbances in radar waves. Passive detection systems use enemy emissions, for example, radio or infrared signals, to locate targets without actively emitting signals. Counter-drone technology employs specialized radars and sensors designed to detect and neutralize small, fast, and low-flying UAVs. 5. Integration with command and control, C2. The detection and tracking data is fed into the command and control, C2 system, where decisions are made. Threat prioritization based on the level of danger posed. Coordination of interceptor systems to neutralize the threat efficiently. Communication with allied systems for a unified response in integrated defense networks. By leveraging these technologies and processes, air defense systems ensure rapid, accurate, and effective responses to a wide range of airborne threats, safeguarding both civilian and military. Target neutralization in air defense systems. Once a threat is detected and tracked, the next critical step in air defense is neutralizing the target. This process involves sophisticated technologies and strategies designed to intercept and disable or destroy the threat before it reaches its intended target. The effectiveness of target neutralization depends on the precision of tracking data, the capabilities of the interceptors, and the speed of response. Neutralization begins with launching an appropriate countermeasure based on the nature of the threat. Missile launch. Surface-to-air missiles, SAMs, are the most common interceptors used to neutralize airborne threats. Missiles are guided by radar or infrared tracking systems to lock onto the target and follow its trajectory. Interception techniques. Proportional navigation. The missile continuously adjusts its course to minimize the angle between itself and the target. Kinetic kill. Interceptors collide with the target at high speed to destroy it. Explosive warheads. Missiles detonate near the target, releasing shrapnel or a directed blast to disable it. Different countermeasures are used depending on the threat type and defense system capabilities. Missile-based systems. Used against high-speed aircraft, ballistic missiles, and cruise missiles. Example: Patriot missile systems intercept incoming threats at various altitudes and ranges. Anti-aircraft guns. Engage low-altitude, slow-moving targets like drones or helicopters, often equipped with radar-guided targeting for improved accuracy. Directed energy weapons, deabuse. Lasers and electromagnetic weapons disable electronic systems or destroy targets directly. Effective against drones and other small, agile targets. Electronic countermeasures. Jamming or spoofing systems disrupt the guidance and communication systems of incoming missiles or drones. Jamming or spoofing systems disrupt the guidance and communication systems of incoming missiles or drones. Jamming or spoofing systems disrupt the guidance and communication systems of incoming missiles or drones. Create confusion, causing the threat to miss its target. Air defense systems often face multiple simultaneous threats, requiring efficient prioritization. Threat level assessment. Based on factors such as proximity, speed, trajectory, and potential damage. High-priority threats like ballistic missiles are addressed first. Resource allocation. Multiple interceptors may be launched to ensure the destruction of critical threats. Decoys or less critical targets may be ignored or addressed with simpler countermeasures. Modern threats, such as hypersonic missiles, stealth aircraft, and swarm drones, demand advanced neutralization strategies. Hypersonic missiles. High-speed interceptors and advanced radar systems are used to predict and intercept their rapid trajectories. Stealth technology. Low-frequency radars and infrared tracking are employed to detect and target stealth threats. Swarm drones. Automated gun systems, electronic disruption, and high-energy lasers neutralize large numbers of small, coordinated threats. After a threat is neutralized, the system assesses the outcome to ensure the airspace is secure. Damage assessment verifies whether the target has been completely neutralized or requires further action. Recalibration adjusts tracking systems to monitor for potential secondary threats or debris. Data analysis evaluates the engagement to improve future interception strategies and system performance. By employing these advanced neutralization methods, air defense systems protect critical assets, civilian populations, and military forces from a wide range of airborne threats. Their ability to respond quickly and effectively ensures the security of airspace in increasingly complex combat environments. Air defense systems are categorized based on their range, operational environment, and the types of threats they are designed to counter. Each system plays a unique role in creating a multi-layered defense that can address diverse aerial threats. These systems are designed to engage low-altitude threats within a limited range, such as drones, helicopters, and low-flying aircraft. Range, typically up to 20 kilometers, 12 miles. Examples: man-portable air defense systems, MANPADS; lightweight, portable systems like the FIM-92 Stinger or SA-18 Igla; short-range missile systems, mobile systems like the Panzer S-1, which combine missiles and guns for versatility. Applications: protecting ground troops in combat zones, defending critical assets like military bases or convoys. These systems provide coverage for larger areas and counter a broader range of threats, including faster aircraft and cruise missiles. Range: between 20 kilometers and 100 kilometers, 12 to 62 miles. Examples: NASAMS, National Advanced Surface-to-Air Missile System, effective against both aircraft and cruise missiles. Buk-M2, a Russian medium-range system capable of engaging multiple targets. Applications: defending airfields, cities, and regional infrastructure, supporting layered air defense strategies. Designed to intercept high-altitude and long-range threats, these systems form the backbone of a nation's air defense network. Range: over 100 kilometers, 62 miles, with some extending to 400 kilometers, 248 miles, or more. Examples: Patriot missile system, USA, known for its effectiveness against ballistic missiles. S-400 Triumph, Russia, capable of engaging aircraft, cruise missiles, and ballistic missiles at long ranges. THAAD, Terminal High Altitude Area Defense, focused on intercepting ballistic missiles in their terminal phase. Applications: national airspace defense, protection against strategic threats like intercontinental ballistic missiles, ICBMs. IADS are comprehensive networks that combine multiple types of air defense systems into a cohesive layered defense. Key features: centralized command and control, C2, systems that integrate radars, interceptors, and sensors. Capability to engage threats at all altitudes and ranges simultaneously. Examples: Israel's Iron Dome, effective against short-range rockets and artillery shells. Aegis Combat System, a naval-based IADs with missile defense capabilities. Protection of large regions or national airspace. Coordination of diverse systems for optimal resource utilization. These systems target specific modern threats, such as drones, hypersonic missiles, and stealth aircraft. Anti-drone systems. Combine radar, electronic jamming, and directed energy weapons to neutralize UAV swarms. Counter-hypersonic systems. Under development to address the challenges of intercepting high-speed, maneuverable threats. Low-frequency radar systems. Specialized radars for detecting stealth aircraft that evade traditional radar detection. Air defense systems designed for naval platforms protect ships and fleets from airborne threats. Fleet protection in open seas. Defending strategic maritime zones. Emerging systems aim to provide global and space-based defense capabilities. Early warning satellites. Detect missile launches and provide early warnings. Space-based interceptors, future. Potential systems to destroy threats during their boost phase in space. Strategic applications. Defense against intercontinental threats and global missile systems. By deploying these various types of air defense systems, nations can create a multi-layered, adaptive defense that counters a wide spectrum of threats, ensuring the protection of both civilian and military assets. Air defense systems are the cornerstone of national security in an era where aerial threats are increasingly sophisticated and diverse. From intercepting high-speed missiles to neutralizing drone swarms, these systems represent a synergy of advanced technology, strategic planning, and real-time decision-making. By integrating detection systems, command and control networks, and interceptor platforms, air defense ensures the protection of airspace, critical infrastructure, and civilian populations. Ultimately, air defense systems are not just a means of protection, but also a deterrent, signaling strength and preparedness to potential adversaries. Their continued development and deployment are vital to maintaining peace and security in an increasingly complex and contested global